Here in this lecture we are going to discuss perturbation theory. Now, what is perturbation? Suppose we have a state, something like this. This state is unperturbed. Perturbed means unperturbed means not disturbed. Not disturbed state, undisturbed state. Okay, there is no disturbance has occurred in this state, so this is called unperturbed state, and this state will have a wave function psi. Let us represent the unperturbed, that means it is not perturbed, the perturbation is zero here. Okay, so psi naught represent unperturbed wave function psi naught, and corresponding to that we have the Hamiltonian, which represent the energy H naught as the unperturbed energy. Okay, now due to some intervention, this state is being perturbed. So for example, earlier this was a rectangle, now it is some way it is deformed. Okay, so this is deformation is called perturbation, or the disturbance caused by some external agency. This external agency has the perturbation H dash. So this perturbation is being induced into this unperturbed state, and we are getting a perturbation and perturbed state. Perturbed state means the disturbed state. So the perturbed state has the wave function psi dash and a corresponding Hamiltonian H dash. Or we will generally represent it as H and the wave function psi, because let us represent the perturbation as H dash. So we can write the perturbation or perturbed state H is equal to unperturbed state or the unperturbed energy plus the perturbation. This is the Hamiltonian, what is right now present. The Hamiltonian is this was the earlier Hamiltonian, and this is the induced Hamiltonian. Okay, now we can represent the perturbation H dash as, let me write this as H dash, that is the perturbation H dash as lambda times, this is the order of the perturbation H1. So we will represent as the first order perturbation. Lambda represent the order of the perturbation, and in the bracket we have written 1, that represent the order of the perturbation, plus lambda square H2. So this is the second order perturbation, and now we have the third order perturbation. Now it goes on, it extends, because this perturbation doesn't end here, because due to this H dash, this has changed in this form. Again, due to this a change in the formation here, or the form has changed, there is another perturbation occurring due to its effect. So effect keep on increasing, right? So now we can write the total Hamiltonian H, that is what we have written earlier. H is equal to the H naught, the initial Hamiltonian, plus what is given as H dash. What is H dash? H dash we are writing in terms of different order perturbation. So H naught plus lambda times H1, that is the first order perturbation, plus lambda square H2 plus lambda cube H3 plus etc. Now this is the total perturbation in Hamiltonian. Hamiltonian is something that gives the energy of the state. So this is the total perturbation in Hamiltonian. Now let us see what is the total perturbation that is occurring in the wave function. So let us write the total perturbation in wave function. So definitely when there is a change in energy of a certain state, it will its wave function also will change. So total perturbation in wave function is equal to, let us write the total perturbed wave function as psi, equal to, that is the initial, which is unperturbed wave function, plus lambda times first order correction to the wave function, plus lambda square psi 2 plus lambda cube psi 3 etc. So what about this energy? So total perturbation in energy, how we can write as E is equal to E naught plus lambda times first order correction to the energy plus lambda square times second order correction plus lambda cube times the third order correction, and it goes. So here is the total perturbation in Hamiltonian, the first equation. The second equation states the total perturbation in the wave function, and this third one, energy, that is the total perturbation in the energy. Now let us write down the perturbed wave function psi equal to psi naught plus lambda times psi 1 plus lambda square times psi 2 etc. Now the energy is equal to E naught, this is the perturbed energy, E naught plus lambda times E naught E1 plus lambda square E2 etc. Corresponding to the wave function, the Hamiltonian is H is equal to H naught plus lambda times H1 plus lambda square times H2. These all are the order of the perturbation. Now we know H psi equal to E times psi, where E is the eigenvalue. Now let us focus on the left hand side. Let us write down what is H. H is equal to H naught plus lambda H1 plus lambda square H2 etc. times psi. what is psi? Psi is psi naught plus lambda psi 1 plus lambda square psi 2, etc. Now h naught will go with psi naught plus h naught into lambda psi 1 plus h naught into lambda square psi 2 lambda square psi 2. Now plus lambda h dash, sorry, h1. So we have multiplied with h naught with all the terms. Now we will go with the second term in here. So lambda h dash will go with psi naught. Okay, fine. Now lambda h dash will go with lambda psi 1 plus lambda h dash will go with lambda square psi 2 plus lambda square h2 will go with psi naught plus lambda square h2 will go with lambda psi 1 plus lambda square h2 will go with lambda square psi 2. So it goes on. Now here the unperturbed state should go with, can only have commutation with the corresponding to that particular order. So we can write lambda naught h naught psi naught plus lambda 1. So whenever we have lambda 1, you can use this one, naught and psi 1. So it is h naught psi 1. Okay, then wherever we have lambda, just take it out. So plus lambda into h1 psi naught plus, here we have lambda square h naught psi 2 plus, here we have lambda square, you can write h1 psi 1 plus, here we have lambda square h2 psi naught plus, here we have lambda square, but look at the power here, this is 2 and this is 1, so this is lambda cube h2 psi 1 plus, this is lambda power 4 h2 psi 2. Okay, now this goes on. Now we will write in short form, that is h naught psi naught plus lambda power 1 into h naught psi 1 plus psi naught or h1 psi naught. Okay, these two values. Okay, this is also included. Now plus, now we have lambda square. Here either it has to be h naught psi 2 plus h1 psi 1 plus h2 psi naught. Now I hope you understood how to write the terms. This is h naught, the sum of the superscript has to be equal to the power of the lambda. So it is lambda power 1. So this is 0 plus 1. This is 1 plus 0. This is lambda square. So 0, 2, 1, 1, 2, 0. So suppose if you have lambda cube, so how we can write that? It will be starting from h naught psi 3 plus h1 psi 2 plus h2 psi 1 plus h3 psi naught. So this is how our terms. So this is the first order correction, this is the second order correction, this is the zeroth order correction, that is the unperturbed energy, and this is the first order correction. Here is the second order, this is the third order. See, this superscript will tell you the order of the perturbation. So similarly we can write it for, we have just written for h psi is equal to E psi. Now we can similarly write it for the right hand side, which will be as follows: lambda naught times E naught into psi naught plus lambda 1 E1 psi naught plus E naught psi 1 plus lambda square, the second order correction, E2 psi naught plus E1 psi 1 plus E naught psi 2. Now for the clarification, lambda cube, the third order, E3 psi naught plus E2 psi 1 plus E1 psi 2 plus E naught psi 3. So this is how we can write the perturbation in energy. For lambda power 0, we can say it is the zeroth order perturbation. Zeroth order perturbation. Zeroth order perturbation is simply means unperturbed state or unperturbed value. Now this is given by from the first one, that is E naught psi naught equal to h naught psi naught. Now for lambda power 1, this implies the first order perturbation. First order perturbation. h1 psi naught plus h naught psi 1 equal to E1 psi naught plus E naught psi 1. Now similarly for lambda square gives the second order perturbation. We can write h naught psi 2 plus h1 psi 1 plus h2 psi naught equal to E naught psi 2 plus E1 psi 1 plus E2 psi naught. So this is the second order perturbation. Now let us see the first order perturbation, that is the correction to the energy. First order correction to energy. This is given by En1. So this 1 represents the order of the correction. Then En represents the state, at what is the state of the system. Now this is given by psi n naught h dash psi n naught. Now psi n naught, both are the initial states, and h dash is the perturbed energy, Hamiltonian. This is also given by simply the expectation value of h dash, or if I can represent this n with the state h dash n. Now in integral form we can write this in this particular form: integral psi n star h dash psi n dx. If it is one dimension, it is dx. If it is two dimension, dA. Three dimension, dτ. So this is how you can find out the first order correction to energy. You can either use this or the integral method. Now here let us see few of the commonly used or commonly available perturbed Hamiltonian in our different systems. For a charged particle, in electric field E, you can write the perturbed Hamiltonian H dash is equal to QEX, where X is the position operator, E is the electric field, and Q is the charge. Now for normal Zeeman effect, the H dash is equal to minus mu L into B bar dot B bar. So that's equal to GL E divided by 2m B into LZ. GL is a constant corresponding to the orbital angular momentum. E is the charge, electric charge. M is the mass. B is the magnetic field. LZ, the angular momentum corresponding to Z axis. Now for anomalous Zeeman effect, H dash is equal to GJ E divided by 2m B into LZ. Now Gj is the constant corresponding to total angular momentum, where J equal to L plus S, which is orbital angular momentum and spin angular momentum, and B is the magnetic field. As we have seen, we are just once again writing the first order correction to the energy. First order correction to energy, that is En of 1 is equal to psi n h dash psi n. Now this is, we can write it in integral form, psi n star h dash psi n dx. Now this limits, what are the limits? Limits are where the perturbation exists. Perturbation exists. Or simply you can write limits of h dash. Limits of h dash. Now for a constant perturbation, now let's write here the first one, that is constant perturbation. Constant perturbation, let us take an example, h dash equal to some b. Now then the first order correction En of 1 is equal to, let us write down here, this is En h dash b, sorry, h dash n, this is equal to n b n, because we know that h dash is equal to b. Now since b is constant, because this is a constant perturbation, we can write this equal to b into n. Now this n is nothing but 1, because this is n is nothing but integral psi n star psi n dx. This is nothing but the total probability equal to 1. And since b dash has limits, we can say the En dash or En of 1 is equal to constant into probability. Because psi n star psi n dx is nothing but probability. Instead of writing 1, we can write p as probability, because the maximum value of probability is 1. Since the limits of perturbation is the limits of h dash instead of the entire limit, it is better to go with the probability. So we can write the constant of for a constant perturbation, the first order correction to energy is given by that particular constant into probability. The other kind of the perturbation is h dash is equal to b times x, some constant into x or some constant into x square. So this is perturbation depending on the uh, position. Okay, so here we have position x, this is x square. So our aim is to find the first order correction to the energy En of 1. So we can write this as n h dash n, so that's equal to n h dash, we can write it as bx times n. Now similarly we can take this out, b which is constant, so it will be n x n. This is nothing but the expectation of x, so b times expectation of x as the first order correction to the energy. Similarly, if it is h dash is equal to bx squared, then En, first order correction to energy, is given by n bx squared n. So that's fine. We will get b which is constant, n x square n. Now that's equal to b into expectation of x square. So this is another value, and please remember that the expectation is within the limits of h dash. Even here we have the limits of h, that is perturbation. Here the next session is finding out the first order correction to the wave function. First order correction to wave function. Wave function psi. Now this is represented by psi for the nth state, the first order correction, equal to sum of m not equal to n psi m h dash psi n into psi m divided by En naught minus Em naught. So this is the first order correction to the wave function. This also we can write it as sum over m not equal to n m h dash n by En naught minus Em naught into m. So now let us see the second order correction to energy. For formula for the second order correction to energy. We have seen the first order correction to energy, which was written by, it can be written as En of 1. Now we have the second order correction, which is given by En of 2. That's equal to sum m not equal to n, the magnitude of m h dash n whole squared divided by En naught minus Em naught. So this is the second order correction to energy. M and En are the different states. En naught is the energy of the unperturbed energy in the nth state. This is unperturbed energy in the mth state. Okay. So with the final few notes we can wind up the perturbation. So the first one, that is first order correction to energy. First order correction to energy depends on sign of the perturbed Hamiltonian. Depends on sign of the perturbed Hamiltonian. Now the second one is spacing between the energy levels. Spacing between energy levels remains same. This is important. Remains the same before and after perturbation. Before and after perturbation. Now here is a clause. This you have to remember, that the perturbation should not depend on n. N is the order. If it depends on n, the energy levels may vary. But if, as long as it doesn't depend on the order, state of the state, that means the in which state our system is in, then it does not depend on the state.